right, today we're going to talk about a specific type of diode known as a tunnel diode. A tunnel diode is actually really cool. It uses the quantum mechanical effect of tunneling to provide a current, and they work a little bit differently than PN junction diodes, but they are an actual type of PN junction diode. These are also called Esaki microwave diodes because of their use at really high frequencies. So a tunnel diode is a PN junction diode in which both the N and the P regions are degeneratively doped. What this does is it causes the Fermi level on the N side to be above the conduction band, and it causes the Fermi level on the P side to be below the valence band. This makes the depletion region really, really narrow, so the probability of quantum tunneling is made as maximal as it possibly can. What this results in is a kind of an odd characteristic in which the current voltage causes the resistance initially to be positive, but then there's an area in which increasing voltage causes decreasing current. So that actually makes an area of negative resistance, which we'll look at in a second. The tunnel diodes were first produced by Sony in 1957. They are still made today, but they are not made in really large numbers, and you pretty much are hard-pressed to find them just in a regular catalog. You can find them, but there's a different way you have to actually get them. So how do they work? Well, basically, you have the degeneratively doped regions. So you notice the Fermi level on the conduction side is higher than the conduction energy, so it's right here. And then the Fermi energy on the P side is below the valence band. And there are electrons sitting in the conduction band ready to go because the Fermi level is so high. But at zero bias, they're obviously not going anywhere. So everything's just kind of sitting, which is what we get when we're at thermal equilibrium. Now, if the voltage is increased a little bit, just a slight forward voltage, we get tunneling. We don't get a lot, but some electrons are able to move to the valence band and cause a current to flow. If the voltage is increased a little more, you get even more tunneling current because there's more space for the electrons to go through the depletion region. Then, as we increase the voltage further, the Fermi level is pushed up such that less electrons can go through again. So now you get a decrease in current, even though there is current still flowing. Then when we get to the point where we add an even larger voltage than that, the normal voltage that we would use to try to forward bias the diode, then you get increased current, no tunneling, and you get the diode performing as it would perform as any other diode. If you reverse bias these, the holes pretty much just fall into the conduction band without much trouble, so more energy just causes more holes to move. Again, this is majority carrier current, not minority. So, advantages that occur, first of all, the forward current is due to majority carriers. So the diode can change really quickly, and that's why it was often used as a switching diode, because it can switch back and forth really, really easily. It doesn't consume much power. The negative resistance area can be useful for amplifiers and oscillators. They have a really, really long life. They last longer than most other semiconductor devices, and they can handle really high frequencies, which if one is trying to use radio frequencies or microwave applications, they're really good. Disadvantages. Well, the output voltage swing is really, really low because it's a diode. The power output is limited because the applied DC voltage, if you want to get in this tunneling area, has to be less than the band gap potential. So you know the forward biasing voltage of diodes tends to be relatively small. So this is a definite disadvantage. The negative resistance region is really, really narrow because it's just in that area before we reach the band gap potential and it's fully forward biased. So that's a very narrow region to find. And also the devices aren't easy to reproduce accurately. So you can't produce a lot of them inexpensively. So initially, tunnel diodes were really promising because they had high speed and they could handle high frequencies, and they were used in oscillator and amplifier type circuits. But over time, other devices have been developed to replace them, basically because of the power range. So nowadays, impact diodes are used in microwave oscillators. So these would be a type of diode that is degeneratively doped at either end. So the P and the N region are degeneratively doped, just like in a tunnel diode. But there is an avalanche and drift region that is put between them that changes the characteristics of that diode. And no, we're not studying that diode. So don't worry about trying to remember how it's constructed. It's just so that you've seen one before. For microwave amplifiers, often field effect transistors are used. We will talk about a type of field effect transistor in this class later, but not right now. So why are tunnel diodes still used? Why am I actually even talking to you about them? Well, aside from being cool, they're really good in military applications because there's all kinds of conditions that the military encounters that aren't encountered by regular people. So you have magnetic fields, you have radioactivity, you have really high temperatures depending on where you are. So they are useful there, and they are actually very long-lived and very reliable. So they do still exist. The circuit symbol is shown on the right. On the left are a couple of actual tunnel diodes. Those are strip line packaging, so that's why the package looks a little weird. But they are marked. The anode end of every diode is always at the back of the big arrow, and the cathode end is always at the front. And then the plus and the minus tell you the direction of forward biasing. So there's actually two different ways of determining how the diode is constructed. So if you can get hold of one of these, and I actually did, you can use something called a curve tracer to show the current voltage characteristics. This is a Tektronix 571 curve tracer. I believe it was manufactured in 1989, but it still works just fine. It has a lot of different places that you can put different types of devices here. And the one we use is, of course, in the middle where the diode is, and it labels actually the cathode and the anode for you. So if you can figure out the cathode and the anode of your device, you can plug it in and you can actually get the characteristic traits. So if we were going to use a regular diode, we would put it in. This is a regular silicon diode. We would put it in, we would make sure the cathode end is in the C and the anode is in the A part. And then we just basically hit start. And you'll notice that the symbol for a regular diode, the plus actually goes in the anode end and the minus goes in the cathode end. And then when we press the button, we have automatically how the current and the voltage relate. And for a silicon diode, the forward bias voltage is about 0.7 volts. It can increase a little past that. And you notice this graph goes all the way up to 20 milliamps. So this is a very typical trace for a regular silicon diode. You can still get tunnel diodes. You can get gallium arsenide Russian military diodes on eBay, and you can get the data sheet, but the data sheet is all in Russian. So on the left is what you get when you get tunnel diodes from eBay. They get sent from the Ukraine. And then the data sheet is impossible to read unless you know Russian, except for the diagram that tells you where the anode and cathode are. They do not mark anode and cathode, but it is marked plus and minus. So that tells us where the anode and the cathode are. We can take that and plug it into the curve tracer, And when we do that, we connect it up such that the anode and cathode are connected correctly, and what we get is a pretty good representation of how the tunnel diode works. You notice there's a negative resistance region between about 0.1 volts and about 0.6 volts-ish, something like that. And then after you get to that voltage, then you have positive resistance as normal. This is a gallium arsenide diode, so the forward bias voltage is about 1.2 volts, so that is reflected on this. Notice that this only goes up to 2 milliamps, so if I were to allow it to go up to 20, you wouldn't be able to see the characteristics. So this is just a short introduction to a type of diode that in all practicality you probably won't encounter. It's just super cool.